Assalamualaikum warahmatullahi taala wabarakatuh dan salam sejahtera untuk semua. Okay, we continue our lecture for today with melting temperature. Okay, look at the definition of the melting temperature. It is a temperature at which crystallinity breaks down and the polymer chain can move freely past to one another. Okay, actually for the crystalline melting temperature, above Tm, the crystal mats and polymer will flow. Okay, mostly crystalline polymer are stiff, strong, harder than amorphous polymer. So most crystallizing polymers are semi-crystalline. That is, a certain fraction of the material is amorphous, while the remainder is the crystalline. Okay. So the reason why polymers fail to attain 100% crystallinity is because of the kinetics, resulting from the inability of the polymer chains to completely disentangle and line up properly in a finite period of cooling or annealing. So we can determine the percent of the crystallinity for polymer by using the microscope, right? And we can observe the what we call the stage in the thermogram by using differential scanning calorimetry or DSC. Okay, by using the DSC instrument, we can observe the heat of the whole sample, which is the heat of fusion per mole of the crystalline material, and we can estimate by the peak of the melting point. Okay, for example, let me show you the graph, overall graph. Okay, this one is, for example, the graph from DSC instrument. We can see the peak of Tg that will appear first on the thermogram. Okay, the graph we call it as a thermogram. Okay, the first peak will appear is Tg. Okay, the value of Tg is right in the center of the graph incline. Right, and then the peak after Tg is the cooling temperature, which is can observe right here. And the last one is the melting temperature. Okay, so it depends on the thermogram. If the Tg is going downward, so the Tc will go upward, and the Tm ratio apa panggil ni peak dia macam deep below. Okay, kalau TG dia macam ke arah naik sikit, incline macam ni, and the TC dia akan dip upward. Okay, so TM dia akan dip ke bawah macam tu. Okay, depends on the graph. Okay, we look at the other graph. Okay, this one is the TG temperature. Okay, TG temperature right here. Dia turun ke bawah, tadi contoh dia ke atas kan. So second option, TG might be the graph might be decline, okay, ke bawah sini, and then kalau dia turun ke bawah, and then TC will show some upward dip macam ni, dia akan naik macam ni, and TM akan dip below. So sebenarnya graph ni dia combine. Okay, yang merah ni dia combine untuk 3 graph. Okay, pertama sekali dia akan tunjukkan bacaan TG dekat sini. Ni guna mesin DSC. And then bila dah lepas stage TG, dia akan di-heatkan. Kan? Dia akan di-heat sampai dia reach melting temperature. Okay. So, lepas dia reach melting temperature, dia akan undergo cooling balik. Dia akan cooling. So, bila dia cooling, dia akan tunjuk peak dekat sini. Okay. Dia akan tunjuk peak kat sini. Alright, we continue with our slide. This crystallization tendency have a large effect on the thermal, mechanical, and other important properties of the polymer. So when polymer is crystalline, It has more stiffer, stronger, harder than amorphous polymer. So polymers are never perfectly crystalline but contain disorder region and crystallites of varying size, depend on the type of the cooling. So if you choose a rapid cooling, the crystal will become more larger compared to the slow cooling, because if you use the slow cooling method, which when you use a low temperature to cool the polymer, and the low temperature, not the low temperature, I mean the slow cooling means that the duration of the period, or the period of the cooling, is extended compared to the rapid cooling, so you can produce a small crystal and many crystal. Okay, we prefer a small crystal size. Factors that influence the melting temperature is also the same factor that influence the glass transition temperature. For example, condition of crystallization, chain flexibility, the symmetry, the interaction between chain or chain segment, tacticity, branching, molar mass, and comonomers. When we look at the condition for crystallization, the rule of thumb, polymer can crystallize in a temperature range from at least 30 degrees C above Tg to at least 10 degrees C below Tm. And the rate of cooling, polymer in principle crystallize relatively slow due to the entanglement of polymer chains with one another, especially when compared to most smaller molecular substances. Thus, it is possible to control the degree of crystallization by adjusting the rate of cooling. So the slow rate of cooling, melting temperature range is narrow. So we prefer a slow cooling so that we can produce a narrow peak of Tm. If we have a rapid cooling, it will show a broad melting temperature, which must be avoided. Okay, but it is actually depends on the application of the polymer itself. Okay, in rapid cooling, it leads to the formation of many crystallization nuclei, and thus also to large number of small crystal. Small crystal have a large surface to volume ratio and thus have a relatively large surface energy. As a result, small crystal leads to low Tm, and the rapid cooling thus leads to the Tm being reduced by up to 30 degrees C. It also leads to polymer with a broad melting range because crystals of very different size form, each of which have their own unique melting temperature. So basically, the crystal form is not as small as it is said, because it has a many size of the crystal, and mostly rapid cooling will produce high crystal size compared to slow cooling. Okay, for too low temperature, the mobility of the chain segment is insufficient to allow the crystallization. If we use the too high temperature, the segments are too mobile for any crystallization to take place, means that they have more energy to move. So it takes time for the crystallization to take place. We look at the next slide. Factors affecting the melting temperature is the change flexibility. The flexibility of the polymer chain has a substantial influence on its crystallization entropy. Okay, entropy. What is entropy? This is actually the thermodynamic. Okay, entropy is given by symbol S. This is the thermodynamic property that describe the amount of the molecular randomness or disorder in a system. Okay, it is actually a state thermodynamic function, meaning that its value does not depend on the path used to arrive at a specific set of conditions. So each system with a specific temperature, pressure, and composition has a unique entropy value. So as the temperature of a perfect crystal increases, the random vibrations of the molecule will decrease, and at the melting point, entropy of a system increases abruptly as the compound transforms into a liquid. Okay, for a comparison between the solid, liquid, and gases, it has a different entropy. Okay, kalau crystalline solid, dia ada highly ordered structure. So, dia punya entropy is very low. And for liquid, it has a higher entropy because it is less order, but all the particles are still found at one end of the container. And the last one, the gas phase, it has the highest entropy because the particles are randomly distributed throughout the entire container. Okay, the crystalline state is more order than the melted state. Okay, crystalline state is given by the symbol Tc, and melted state is melting temperature is Tm. This loss of entropy is more pronounced the greater the number of conformation that the polymer can adopt in its melted state. This number is in turn dependent on the differences in energy between the trans and gauge conformation. If this energy differences is small, the polymer tends strongly to coil up on it. Okay, the gauge transition or the gauge state is slightly unstable compared to the trans position or trans state. And the greater depth of the transposition indicates that this is the position of maximum stability. Although the gauge states are slightly less stable, all the three minima can be regarded as discrete rotational states. So we have eclipse position. We have a staggered formation of the chain. Okay. Thus, the conformational entropy in the melt is large and the change in entropy on crystallization very unfavorable. So this is only overcompensated by the crystallization enthalpy at lower temperature. Okay, polymer chains that have a small differences in energy between their trans and gauge forms generally have low melting temperature. Because the crystallization enthalpy for high-density polyethylene and PTFE are very similar, the difference in their melting temperature is a result of the greater tendency of polyethylene to form coils and is thus an entropy effect. You can see that this is the energy differences, which is the trans or gauge. For PE, we have 3 kilojoule over mole, and the melting temperature is slightly lower than the PTFE, which is they have 18 kilojoule per mole. And melting temperature is 372, which is slightly higher because of the difference in the energy. And PTFE has higher energy compared to polyethylene, okay, which leads to increase the melting temperature. In terms of symmetry, a symmetrical element in the polymer backbone means that polymer chain can no longer fit so well into the crystal structure. The resulting disturbance to the organization of the crystal leads to a lowering of the melting temperature. This effect is especially marked for structural units that leads to a kink in the polymer chain. Example of these are cis double bond, cis connected ring, or aromatic ring, which have a polymer backbone chain linked to them at their auto or meta position. So symmetry related disorder leads, for example, to trans polybutadiene being crystalline with a melting temperature, where cis polybutadiene is an amorphous. So the symmetry of the element at the backbone, it will affect the melting temperature itself. Okay, if the asymmetrical element is cis, so it will be lowering the Tm, and if it has a trans asymmetrical element, so it will produce a high Tm. In terms of the interaction between the chain, a good interaction between polymer chain